Magnetism is our next chapter, and magnetism is a very important chapter because it has so many real life applications. The iPads, the iPods, the computers, the laptops, the recording devices, all this would not have been possible without the ideas of magnetism. So in this chapter, we're going to look at many of these ideas, and it's a detailed chapter, but we will start with the basic properties of magnets. We will see how magnetism can be used to build generators. We'll talk about magnetic resonance imaging in detail, probably in a new video. And we will first start with the properties of magnets. Number one, all magnets have two poles, the North Pole and the South Pole. And it's important to note that you cannot produce a single pole. So if you take a magnet and you divide it into two, you break it into two, you're going to get two magnets. You continue breaking this up to the atomic level, you're going to continue getting magnets. That means you will always have the North Pole and the South Pole. A single pole cannot be isolated, at least not yet. So that's a big difference between magnetism and electric charges. You could have a single isolated charge, like a positive charge, a negative charge, but you cannot have a single pole. They always appear in pairs. Second property is that our Earth is a magnet. So the Earth behaves like a huge magnet. So it has a North Pole and a South Pole. So that means when you suspend a magnet, you see that the magnet lies along the north-south direction, and the South Pole of the magnet, the South Pole of the suspended magnet, actually points towards the North Pole of the Earth magnet. Okay, and you can also see that the geographic North Pole and the magnetic North Pole are not exactly at the same point. So if this is the geographic North Pole, then the magnetic North Pole is about here. So they're not exactly the same. Now this could have been a disastrous result for sailors, so many centuries back when they used the magnet as a compass, because they thought that it actually points to the geographic North Pole, which could have taken them away from the location that they were looking for. So that's the second property. The Earth behaves like a magnet. Number three, I think I already discussed this. Breaking a magnet into two always produces magnets, smaller and smaller magnets all the way to the atomic level. Okay, so you cannot isolate a single pole. I can't stress that enough. Number four, the atoms in all materials actually are tiny magnets. The atoms in all materials are tiny magnets, but in materials like iron that could be magnetized, these tiny magnets can be aligned in one direction. That's why you can magnetize iron, but you can never magnetize wood, because all these tiny magnets cannot be made to line up in one direction. We'll get to that in one of the slides there. So this is what I mean by breaking a magnet into two produces more and more tiny magnets. And magnets come in all kinds of shapes, sizes, and strengths. You could have rectangular magnets, bar magnet, or you could have cylindrical magnets. You also have the horseshoe shaped magnets, the U-shaped magnets, and these are the most powerful form of a magnet, the U-shaped magnet. These are the magnets that are used in galvanometers and ammeters and voltmeters, because they are the most powerful form of a magnet. And then there are three types of materials: a ferromagnetic material, a diamagnetic material, and a paramagnetic material. I think we will focus on ferromagnetic material. The word ferro means iron, coming from ferrous. So ferromagnetic materials exhibit a strong magnetic field. They can be magnetized, and they show a strong magnetic field. And the best examples are iron, cobalt, nickel. These are the three. Number two, when you look at a ferromagnetic material, you see that ferromagnetic materials can be magnetized by bringing it close to a magnet. You can bring it close to a magnet, and you can heat and cool alternatively to make the magnetism stick. So in fact, you can use a simple piece of iron and rub it in one direction on a magnet continuously. So if that's the piece of iron, you continuously rub in one direction, and you can change this iron into a magnet. And when we talk about ferromagnetism, you have ferromagnetic domains or regions within the material that act like small magnets, as you can see here. These are the ferromagnetic domains. Each cell, each region is a ferromagnetic domain. And a ferromagnetic material cannot always be magnetized, because if you keep it above a certain temperature, it cannot be magnetized. So that temperature is called the Curie temperature. The Curie temperature is the maximum temperature, beyond which a ferromagnetic material cannot be magnetized. That means you got to cool it down to a temperature less than the Curie temperature in order to magnetize a ferromagnetic material. Next, we have electromagnets. Electromagnets, as the name implies, is a magnet that only behaves like a magnet when an electric current flows through it. So electric currents always produce magnetism. And so if you have a ferromagnetic material like iron, and you have a coil wound over it, in a simple piece of iron, and a coil wound over it, as long as you pass a current through the coil, the iron behaves like a magnet. It becomes magnetized. When you switch off the current, that is just a piece of iron. So that's called a ferromagnet. It's called an electromagnet. It's called an electromagnet. And ferromagnetic materials are usually used to produce these electromagnets. And electromagnetism, is the use of electric currents to produce magnets. And electromagnets have so many uses. If you want to take scrap metal from a factory out in the yard, you can use electromagnets. Or most of the recording devices like hard disks use electromagnetism in order to magnetize and demagnetize, and to store information in a memory. So that is another use of electromagnetism. All right, and then a ferromagnetic material can be used to make a strong magnet, because the strength of the magnetism depends on the strength of the current. But there are limits to this, limited by the resistance and so on. But a stronger current produces a stronger magnet. So you can use ferromagnetic materials to produce very strong electromagnets. And like I said, ferromagnetic materials can act as memory devices. So that's something that we have to know about electromagnets. And continuing this discussion of electromagnets, understand that electric current is the source of all magnetism. In fact, magnetism is explained using electric currents. And then I can't stress this enough, there are no magnetic monopoles. And since magnetic forces act at a distance, just like we did with electric charges where we had electric fields, with magnets you're going to have magnetic fields. So same thing, you have a magnetic field around a magnet, and the magnetic field shows the strength and direction of the field. If you have lines closer to each other, then you have a stronger magnetic field. For example, the lines here are closer, so that's a stronger magnetic field as compared to the lines here that are further apart, which means it's a weaker magnetic field. So magnetic fields can be shown, or can be drawn rather, to show the direction and the strength of a magnetic field. And also remember that the magnetic field starts from a north pole and does not end on a south pole. It continues to loop around and then flows back to the north pole. So magnetic field lines are closed. This is a big difference between magnetism and electric fields. Electric fields are not closed. They start on a positive charge, end on a negative charge. But a magnetic field is always closed. It begins on a north pole, so to say, and then doesn't stop at a south pole, but continues to loop around back to the north pole. So magnetic fields or magnetic field lines are closed loops. Here are 4 important properties of magnetic fields. The direction is a tangent drawn to the field line at any point. So if you want to find the direction of magnetic field at any point, and you have a magnetic line like that passing through that point, let's say this is the north and this is the south, so you have a magnetic line. If you draw a tangent to that line, you will get the direction of the magnetic field at that point. Number 2, the strength of the field is in proportion to the number of lines that pass through an area. So like I said before, if the lines are closer and if there are more lines passing through a certain area, then it's a stronger field. Number 3, remember, magnetic field lines can never intersect. Magnetic field lines cannot cross each other, because then that would mean that you could draw 2 tangents at one point, which is impossible because you can't have 2 directions for a magnetic field at one point. So magnetic fields will never cross each other. And again, magnetic fields are continuous. They form closed loops without beginning or without an end. They go from the north pole to the south pole, but do not stop at the south pole. They continue to form a closed loop. Now we come to a very important part of this chapter. That is, when a charge moves through a magnetic field, there could be a force acting on that charged particle. So you have a magnetic field and it's set up in a certain direction, and you have a charged particle, either positive or negative, moving through that field, and a force acts on that charged particle. Now let's consider that Q is the charge of the particle. Q is the charge of the particle. Its velocity is v meter per second, and the force acting is F. So the formula for this force is given by QVB sine theta. So the force on a charged particle is given by QVB sine theta, where Q is the charge of the particle, V is the velocity of the particle, B is the strength of the magnetic field through which the charged particle is moving, and theta is the angle between the velocity of the particle and the magnetic field. Now, to make things simple, let's imagine that the theta is 90 degrees. That means if the magnetic field is along the x-axis, the particle is moving along the y-axis. So the velocity is along the y-axis, the magnetic field is along the x-axis, so the angle is 90 degrees. Sine 90 is 1, which means maximum force acts on the particle. What if the magnetic field is along the x-axis and the particle is also moving along the x-axis? Now, what is the angle between the velocity and the magnetic field? Of course, it's 0 degrees. Sine 0 is 0, which now means that no force acts on the particle. So remember, if a charged particle moves parallel to a magnetic field, no force acts on it. And if a charged particle moves perpendicular to a magnetic field, maximum force acts on it. And in this case, the direction of the force is given by the right hand rule. As you can see in the diagram, the right hand rule, where the thumb gives the direction of the velocity, the fingers give the direction of the magnetic field, and when you fold your fingers at 90 degrees, you get the direction of the force. So you have the thumb giving the direction of velocity, the magnetic field given by the fingers, so they are at right angles here, and then when you flip your fingers, that gives the direction of the force acting on the charged particle. All right, so direction is given by the right hand rule, and the formula for force is QVB sine theta. Theta is the angle between the velocity of the particle and the... In fact, we can use this formula to find the unit of magnetic field, which we have not done yet. Remember, units of magnetism are always in terms of the units of current. So when you rearrange this formula, you're going to get B is equal to F by QV sine theta. The unit of force is Newton. The unit of charge is Coulomb. And the unit of velocity is meter per second. Sine theta is just a number and is no unit. So Coulomb per second, here you can see Coulomb per second is called an ampere. Therefore, now we can write this as Newton per ampere meter. So that's the unit of magnetic field strength, Newton per ampere per meter. One consequence is an important consequence where you can have the charged particle continuously move in a circular path. Let me show you that situation. So now if you look at this diagram, you see X is here. This always shows the back of an arrow, which means this represents a magnetic field into the plane of the board, into the plane of the paper. All right, so whenever you see a field, magnetic field represented with an X, that means it's a magnetic field pointing perpendicular to the plane of the paper and into it. So that's the magnetic field. And then you see a charged particle. In this case, it's a negatively charged particle, and that charged particle is moving. It's moving in this direction. Let's say it's entering in this direction. All right, it's entering here. So you have a force acting on it, and using the right hand rule, if you keep the thumb along the direction of the velocity, it's moving that way, and remember that the fingers have to show the direction of the magnetic field, which is that way, and then when you flip the fingers, it has to show the direction of the force. But do not be confused. If you flip the fingers, it will show you the direction of the force upwards, and that is true for a positively charged particle. But since this is a negatively charged particle, you have to, when you get it upwards, You have to remember this is a negatively charged particle, so the force is going to be in the opposite direction. That's why the forces are shown in the opposite direction here. So the direction of the force, using the right hand rule that we looked at, applies to a positively charged particle. Again, so the thumb gives the direction of motion of the positively charged particle. Fingers show the direction of the magnetic field. You flip it, the force is acting in the upward direction if it is a positively charged particle. But if it's a negatively charged particle, immediately you know the force is acting in the downward direction. So because of that force acting, the charged particle is going to curve a little bit because it wanted to continue straight, but there is a force acting down, so it makes it bend down. Now when it bends a little down or moves in the form of an arc, the force also changes. You see, the force now becomes this way, making it further bend, and then the force changes too. So this makes the charged particle ultimately move in a circular path. If the magnetic field is set up in a large enough area, you will get the particle move in a circular path. And we can find the radius of that path by remembering that when anything moves in a circular path, there is a centripetal force acting on it. And the centripetal force is given by mv squared by r. So now we can put those formulas together. We already know F is qvb sine theta. In this case, theta is 90 because particle is entering at right angles to the field. So theta is 90, which makes F qvb, and then this must be the centripetal force, which is mv squared by r. Rearrange that, you get the formula for radius as mv by qb. That's an important formula to remember. And I've given an example here. So if you consider that it's an electron moving, the mass of the electron is 9.11 times 10 to the negative 31 kilogram, and assuming that it's moving at 6 times 10 to the 3 meter per second, then you can calculate the radius by knowing the charge of the electron, and the strength of the magnetic field is, let's say, 0.5 Tesla. You can calculate the radius of the path. The radius of the path comes out to be 6.83 times 10 to the negative 4. Oh, and the velocity is 6 times 10 to the 7 meter per second, not 10 to the 3. So you can see that if it's a more powerful magnetic field, the radius becomes smaller. So if it's a stronger magnetic field, then it makes a smaller circle. If it's a weak magnetic field, it makes a bigger circle, or maybe it just goes through the magnetic field in the form of an arc. So far we were discussing the case of a charged particle entering the magnetic field at right angles. What if the charged particle does not enter at right angles? Instead, it enters at some other angle. All right? It's not parallel, because if it's parallel to the magnetic field, then no force acts on it. Neither is it perpendicular. So it enters at some other angle. Now, let's see what happens in this case. In this case, what's going to happen is the velocity that's at an angle can be broken up into a component that's perpendicular to the magnetic field and another component that is parallel to the magnetic field. Are you with me? So the parallel component, nothing happens to it, and so the particle continues to have that parallel velocity, which will take it forward. But because of the perpendicular component, the particle will begin to move around in a circular path. So now you have a combination of forward motion with circular motion, which makes it a helix. As you can see in this diagram, you see that it has a helical motion there, and That's how we explain what is called the aurora borealis. Check that out, the northern lights, where when charged particles enter the Earth's atmosphere, they keep going around in helical motion, and producing a lot of beautiful light because of the collisions with the air molecules. Right? So charged particles cause collisions with the air molecules moving in spiraling, helical motion, and then produces that splendor of light. Read more about that. Now let us look at what happens if a current carrying conductor is kept in a magnetic field. So take a look at this circuit here. You have a battery and you have a conductor like that, and one part of this conductor is kept in a magnetic field. Right? That's a magnetic field from north to south, and this conductor, which is carrying current I amperes, is situated in that magnetic field. And since we know that current is the flow of charges, and whenever a charge flows or moves through a magnetic field, a force acts on it, obviously this current carrying conductor will have a force acting on it. So whenever a current carrying conductor is situated in a magnetic field, a force will act on it. This ultimately leads to the principle of an electric motor. That's what happens in an electric motor. We'll get there in a minute. But first let's look at the value of the force that acts and the direction of the force. The direction of the force is once again given by the right hand rule. As you can see, in this case the thumb points in the direction of the current. The stretched fingers again give the direction of the magnetic field, and then the palm, or when you switch your fingers at right angles, it gives the direction of the force. The thumb gives the direction of the current, the fingers give the direction of the magnetic field, and the palm, which is now facing up, gives the direction of the force. And the formula for the magnitude of this force is F is equal to ILB sine theta. I is the current that flows in amperes. L is the length of the conductor in meters. B is the strength of the magnetic field. We know that the unit of strength of the magnetic field is Newton per ampere per meter. But let me tell you that it's also called Tesla. So the unit of I is ampere, the unit of B is Tesla, and the unit of length is meter. And again, if the angle is 90 degrees, then sine 90 becomes 1, and the formula becomes F is equal to ILB. As before, if theta is 0, that means if the current carrying conductor is placed parallel to the magnetic field, no force acts on it. So for maximum force to act, the conductor must be kept at right angles to the magnetic field. Now, as a consequence of the force acting on a current carrying conductor kept in a magnetic field, we can build an electric motor. Because if instead of a conductor, you have a coil like this kept between the poles of a magnet, and if you send a current through this coil, like enters in and then the current goes through it and then flows out, there is going to be a torque acting on this coil. And that torque, in fact, makes the coil rotate. So you can see in this diagram why a torque acts on it. Because if you look at the length of the coil here, you will see, this is the length of the coil. You will see that the force acts in one direction on one side because the current is flowing down through that side, while the force acts in the opposite direction here because the current is flowing up in that side. I hope that's clear. The current enters, it flows up this side, and then it flows down on the other side. Because of the change in direction of the current, the forces that act on both the sides are equal but opposite. Now that's what you call a torque. And that makes the coil rotate. And to find out the formula for the torque, torque is tau. We have to remember that torque is given by the distance between the forces multiplied by the force times sine theta. In this case, the distance between the forces is the width of the coil. That's very clear here. This is one force, this is the other force, and the distance between the two forces is the width of the coil. So torque is by definition the distance between the forces times one of the force times sine of the angle. In this case, the angle is 90, and we know that the force is given by ILB, right? ILB, and that's how the sine theta comes in. So I should have just written, so I should have just omitted the sine theta here. Let me correct that right now. So torque is distance times force, but force is ILB sine theta, and you know that length times width, length times width is the area of the coil, isn't it? Length of the coil times the width of the coil is the area of the coil. That's why you see A there, and then it becomes IAB sine theta. Now if the coil has n number of turns, then you got to get the total, you got to multiply this with n, where n is the number of turns in the coil. So ultimately, the torque acting on the coil is given by NIAB sine theta. Again, n is the number of turns in the coil, I is the current flowing through the coil, A is the area of the coil, and B is the strength of the magnetic field. If theta is 90 degrees, sine 90 is 1, and then maximum torque acts on the coil. Now it's easy to really understand the working of a DC motor. And I've shown it here. I've written, when current flows through a loop in a magnetic field, we've seen that a torque acts on it, which makes it rotate, but you got to set it up in such a way that it can rotate continuously without the cable getting entangled. That's what you see here. You see the what's called the brush arrangement, the split ring. It's a ring split into two halves like that, a ring split into two halves, and on either side you have two carbon brushes brushing against it. So when it rotates, it's like it's just rotating, touching or slipping past the carbon brushes. And when the currents are reversed here, because of the brush arrangement, the currents also reverse, which makes it rotate in one direction. If you did not have the brushes and the split ring, then the coil would have gone this way. It would swing back and forth, which is not of much use. So in order to make it rotate in one direction, you got to make sure that the current changes direction exactly when it makes half a turn. That's when you get continuous rotation in one direction. That's the idea of a DC motor. It's called a DC motor because it's direct current or direct current that's flowing through the motor. And now, in order to measure a current or to detect a current, we have what is called a galvanometer. The idea of a galvanometer is the same as that of the motor, except in this case, we do not want the coil, we do not want the coil to continuously rotate. Instead, we want it to move through a certain angle, rotate through a certain angle, which will be in proportion to the current. So in order to make it do that, we need to have it pivoted or suspended, the coil, and then we also need to have a spring. We need to have a spring as shown here, because when you switch off the current, you need the coil to come back to the original position. All right, so same construction as a motor, except that you don't have the split ring and the brushes, because you're not looking to make it rotate continuously in one direction. All right, so when the current flows through it as before, a torque acts on it, and the torque is going to be proportional to the current, because N, A, B are constants. So the torque acting depends on the current. So if you send a bigger current through the galvanometer, there's going to be a bigger torque, which means the coil will rotate more. So that is the idea of a galvanometer. Remember that a current always produces a magnetic field, but the pattern of the magnetic field depends on the shape of the conductor. For example, if you have a straight conductor as shown in the diagram carrying a current, and let's say it's flowing upwards, the magnetic field produced around it will be circular. So you will have concentric circles. That means all the circles have the same center, and the center is going to be on the conductor. You see that? And the direction of the magnetic field could be found out using the right hand rule number 2, where you hold the conductor in your right hand with the thumb pointing in the direction of current, and then the direction of the closed fingers to the tips will give you the direction of the magnetic field. So if the current is flowing up, the magnetic field is circular in this direction. But if the current is flowing down, then you see that automatically the magnetic field reverses direction. So that's how you find the direction of the magnetic field. And the magnitude of the magnetic field is given by, it's surely going to depend on the strength of the current, right? The stronger the current, the bigger the magnetic field, but it will also depend on the distance of the point. So if you're trying to find out the magnetic field here, it's a certain distance at a certain distance from the conductor, so you will have a certain magnetic field there. But if you look at a point further away, surely the magnetic field is going to be weaker. So the strength of the magnetic field depends on the current and the distance. As you can see here, B depends on I, which is the current, and R, which is the distance of the point where you're looking for the magnetic field. And there is a constant that comes in, which is similar to permittivity in electricity. But this constant is called permeability. I know, it's called permeability of free space, because the magnetic field depends on what material you have between the conductor and the point. So usually it's either free space or air, and then you use this constant called mu naught, which has a value of 4 pi times 10 to the negative 7. Look at the units later, it's Tesla meter per ampere, but at least know that the constant has a value 4 pi times 10 to the negative 7 for free space. So that's the formula for magnetic field due to a straight conductor, and the direction is given by the right hand palm rule 2. On the other hand, if the conductor is in the form of a loop or in the shape of a loop, then the magnetic field is as shown in the diagram, as you can see here. And that's again given by the right hand rule. Just take a look at this. You hold your thumb, right hand again, in the direction of the current, and the direction of the fingers will give you the magnetic field. Okay, so If the current is flowing that way, then the magnetic field is upwards, as you can see here. All around it, the magnetic field is up. So you can see a better picture here showing all the lines. You can see all the lines here. All those lines are pointing from bottom to top. And the strength of the magnetic field, or the magnitude of the magnetic field, is now given by the formula B is equal to mu naught I by 2R. I is the current and R is the radius of the loop. Now that's just for one loop. If you have n number of turns, that makes it a coil, then you got to multiply this with n. That is how you find the magnetic field due to a current carrying loop. The third and the final conductor that we're going to look at is a solenoid. A solenoid is an extended coil. It's something like if you have a PVC pipe and you have a coil wound over it with a lot of turns that's extended. That's a solenoid. And the magnetic field produced by the current flowing through the solenoid actually is exactly similar to the magnetic field produced by a bar magnet. You can see that here. And once again, the direction of the magnetic field is given by the right hand rule number 2. Easier to represent the fingers by the current, and then the magnetic field would be given by the thumb. So if the current is flowing that way as given by the fingers, the magnetic field is along the axis of the solenoid this way. That's what is shown here. So you have the magnetic field shown by those blue lines, and you have inside the solenoid, you have the magnetic field going from right to left because the current is flowing this way. On the outside is up and inside down. And the strength of the magnetic field is given by the formula B is equal to mu naught little n I. You got to be careful here because the little n is not the total number of turns. In fact, it is the total number of turns divided by the length of the solenoid. So if you have n as the total number of turns, caps n, and L is the length of the solenoid, you got to divide them to get your little n, which is something that students miss out. So be careful on that. So that's the formula for magnitude of the magnetic field due to a current flowing through a solenoid. Finally, we have a situation where you have two parallel conductors and both are carrying currents. Let's imagine that both the currents are flowing upwards as shown in this diagram. So you have two parallel conductors both carrying currents. This is a tricky situation because the current flowing through the first one is going to produce a magnetic field all around it, right? And the second one is situated in that magnetic field. So a force will act on it because it is a current carrying conductor kept in a magnetic field. Likewise, the current flowing through the second one is going to produce a magnetic field all around it, and the first one is situated in that magnetic field. So a force acts on that one. So that means if you have these two current carrying conductors kept close to each other, there is going to be a force between them. It could be a force of attraction or a force of repulsion depending on the direction of the currents. If the currents are flowing in the same direction, it's attractive, but if the currents are flowing in opposite directions, one up, one down, then the force is repulsion. But in both cases, the value of the force is given by this formula. Mu naught I1 I2 times the length of the conductor by 2 pi r. So let's say we're trying to find the force on the second conductor. So in that case, L would be the length of the second conductor. I1 and I2 are the currents in these conductors. mu naught, as before, is the permeability of free space, and little r is the distance between the two conductors. And this formula actually helps us to define an ampere, because as you can see, if you consider that the currents flowing through both of them are 1 ampere each, and that these conductors are kept 1 meter apart. So we make everything 1 ampere through this one, 1 ampere through the second one, and they are kept 1 meter apart. Then when you plug it into the formula, I1 is 1, I2 is 1, and R is 1. That leaves us with these two factors, and the pi's will cancel out. 4 by 2 is 2, so that gives us a value of 2 times 10 to the negative 7 Newton per meter. It's per meter because you have the length on the other side. I've taken the length to the other side, okay? So that's why it's Newton per meter. This means we can define an ampere using this idea. So 1 ampere is that current which, when flowing through two parallel conductors kept 1 meter apart in free space, of 2 times 10 to the negative 7 Newton acting per meter. I know, and you got to repeat that. 1 ampere is that current which, when flowing through two parallel conductors kept 1 meter apart in free space, produces a force of 2 times 10 to the negative 7 Newton per meter. Now this chapter had a lot of concepts inbuilt. It's a very important chapter, and I hope this video combined with the reading of a textbook will help you see clearly the concepts in this chapter. So good luck on that.